Okay, so the goal is to try to use the analytic continuation that we've done and use this to understand what's going on with the Riemann zeta function, as well as try to get this to track, which hopefully one will. All right, if not, all right, slowly track. So I'm not going to go through the full proof of the analytic continuation of the Riemann zeta function, the gamma functions, and whatnot. If you want, it's in the book. You can watch some of my videos from Math379 last semester. I want to just give a rough proof right now of the prime number theorem, but at least a little bit better than the job I did last time in 389. So, proof of the prime number theorem. And it's often abbreviated PNT. A lot of complex analysis was developed to attack problems like this. So it had been conjectured for quite a while as to how many primes there should be up to x. And the main function we study is pi of x is the number of p prime, p less than equal to x. And the belief is this should be about x over log x. Beta is the logarithmic integral, which is the integral from 2 to x of dt over log of t. So the first term of that will be x over log x. The Riemann hypothesis is that the errors are on the order of square root cancellation. This will tie in very beautifully to the central limit theorem that the Riemann hypothesis, the distribution of zeros of the Riemann zeta function, it turns out this is equivalent to how well you can count primes. And if instead of looking at the actual primes, if you look at random primes, the Riemann hypothesis is true with probability 1. So what does that mean? Well, if this is true, if I look up to x, and I have x over log x numbers that are prime, the density of primes is about 1 over log x. So each number has essentially a probability of 1 over log x of being prime. So you can flip a coin, and each integer n is declared to be prime with probability 1 over log n. And this will give you a random sequence. And you can consider the space of all such sequences, and you can ask how many of these sequences satisfy a Riemann hypothesis. It's no longer going to be talking about distribution of zeros of the functions, but errors in counting the number of successes up to x. And almost all sequences will satisfy the Riemann hypothesis because of the central limit theorem. So hopefully this will be a motivation for why we want to do the central limit theorem. This is a great way to build intuition about things in number theory, is you look at random processes that have maybe similar densities and see when must these things hold. Now, unfortunately, the primes are a little bit different than a random sequence of numbers. There's one thing that the primes have that no other random sequence has, and that is unique factorization. So they're the only one, when you look at the corresponding series, where you actually will be able to have this kind of Euler product. And so maybe that Euler product makes things different. We believe it does. We believe it does in a good way. We believe that that's going to help us, not hurt us. But maybe that prevents the Riemann hypothesis from being true. So we start with zeta of s is the sum, n goes from 1 to infinity, of 1 over n to the s, and it's the product over primes of 1 minus 1 over p to the s inverse, at least if the real part of s is greater than 1. What you may have noticed is that I have not given you that much reading to do this week. I've had you skim chapter 8, but not too much reading. Part of it is I want you looking at this a little bit fresh. What should we do to this function?
Well, last class we took the log.
We took the log?
That's it.
When we did two different proofs of the infinitude of primes. We looked at the log of this and we counted, this was basically, we truncated the sum, truncated the product, and we also took s equals 2. So you give us two different proofs of the infinitude. Okay, why else would we want to take a log?
Some product.
Yeah, we've got a product. Whenever you see a product, your immediate thought should be take a log of it. Yeah. If I don't see that on some of the blue sheets or your senior exit interviews, I will be very sad. Always take a product. Always take a log with it when you see a product. But this is complex analysis. We don't just do products. What else do we do in complex analysis? What's the big thing we like to do in this class? Contour integral. So we want to do a contour integral. What function should we contour integrate? It's okay if this is not the final function we contour integrate, but I want a starting function that I should look at. What's a good function to contour integrate? 1 over s is not a bad one. And that's the derivative of the log of s. So you're close. We don't want to quite take 1 over s. What function do I want to? Almost surely has to involve zeta. What function related to zeta should we contour integrate? Not log zeta. Almost though. So go back. Think to the big theorems we had. Think of Rouché's theorem. It's not just the function f that we integrate.
Zeta prime over zeta.
Zeta prime over zeta, the logarithmic derivative, right? Remember, in complex analysis, when we do the logarithmic derivative, we get things that detect happenings at poles and zeros. And if somehow the Riemann hypothesis is related to the distribution of zeros of this function, if we integrate zeta prime over zeta, this is going to hopefully give us a situation where those will contribute. Now, we have two ways to take the logarithmic derivative. This is probably the easiest question I can ask you today. Do I want to take the logarithm of the sum, or do I want to, I can even do this with a straight face. We of course want to take the logarithm of the product, right? This is why we love the Euler product, because in complex analysis, so I can write on the board, in complex, we love logarithmic derivatives. Thus, the Euler product is good. Well, I can do better, it's great. So you can begin to get a sense of why analytic number theory progresses the way it does. Complex analysis wants to integrate a logarithmic derivative. The logarithmic derivative of zeta becomes zeta prime over zeta. So d by ds of log of zeta of s is zeta prime of s over zeta of s. And this is now going to be negative the sum over p of the log of 1 minus 1 over p to the s. And then we have to take the derivative of this. I'll do it slowly. Negative d by ds, the sum over p, the log of 1 minus 1 over p to the s. Okay? So far, so good. What is the derivative of the sum? Some of the derivatives. Alright, so this step has to be justified. If the real part of s is sufficiently large, this should be okay to justify. So, let's say if real part of s is big, the derivative of the sum is the sum of the derivative. And now what we'll get is we'll get negative sum over p. The derivative of the log of this, we're going to get a 1 minus 1 over p to the s down below. And up top we have to take the derivative. We're going to get a negative sign from this, then we have a p to the negative s, we're going to get another negative sign, so the negatives cancel. If you want, p to the minus s is e to the negative s log p. So we'll get a log of p, and then we'll get a p to the minus s. Okay? We can expand this using a geometric series. And this will then become negative sum over p, and then the sum, k goes from 1 to infinity, log of p times p to the negative ks. And that's just from expanding down below. And we start at 1 because we have this extra p to the minus s up top. And so what we're going to do now is we're going to introduce a useful function, the von Maugwald function. Lambda of n is equal to the log of p if n is equal to p to the k for some integer k, and 0 otherwise. Okay, and so this is an extremely useful function to study. Now if you look at what's going on over here, this is going to allow us to rewrite this expression very nicely. And we get this beautiful formula that zeta prime of s over zeta of s, I'll move the negative sign over to this side, is going to equal the sum over n of lambda of n over n to the s. So we have a new series. The zeta function was the sum of 1 over n to the s. The new function is the sum of lambda of n over n to the s. Lambda of n is going to be log of p if p is, log of p if n is a power of a prime, 0 otherwise. What you'll notice is that we've introduced a small amount of discrimination. Small amounts of discrimination are actually very good in mathematics. Okay? I'm being very careful because I know this is being recorded. I'm not saying massive discrimination. I'm not saying I'm going to have weights where the prime is weighted by, say, the square root of p. The logarithm is a very slowly varying function. So the amount that it changes over the regimes we study is going to be negligible. Okay? But the advantage of that is if you look at the zeta function, when you take its logarithmic derivative, logarithms naturally arise. So it's much easier to count weighted primes. At the end of the day, do you want to know how many weighted primes there are up to x? No. You want to know how many primes there are up to x. So what you do is you then remove the weights. And use techniques called partial summation to remove the weights, which are not that bad. So now we want to somehow do a logarithmic integral. Does anybody know, I'm going to multiply both sides by a function. It's going to be related to what we were studying yesterday. What should I multiply both sides by?
X to the s over s.
Excellent. And so now we get negative zeta prime of s over zeta of s, x to the s over s, is equal to the sum over n of lambda of n, and now we'll have x over n to the s, 1 over s. And so now we'll do an integral of both sides. I'm trying to just give you a rough sense of why the prime number theorem is true without going into all the nitty-gritty. Now, we need a really good extension of the Riemann zeta function. We've talked about how you can extend it to the real part of s greater than 0. So we can at least do the integration in the critical strip and push the integration all over to the line real part of s equals 0. We want to keep pushing it further and further and further to the left. And the reason is we want the integration over that final boundary line to go to 0. And if you think about this, if I have a value of x which is large, the further I push this off to the left, the less it's going to contribute. So what we'll start with is we will integrate 1 over 2 pi I, say c minus I infinity to c plus I infinity, zeta prime of s over zeta of s, x to the s over s ds. And now you might have noticed that what letter am I using for complex? S. I'm not using z. And one of my thesis advisors, Peter Sinek, explained to me as follows: until you prove the Riemann hypothesis, you will use Riemann's notation. And so, in fact, if you want to write s, you do not write s as x plus iy, s is sigma plus it. If you want to enrage me, this is just below rooting for the New York Yankees and not mentioning the word area when you talk about the fundamental theorem of calculus. Right? S is sigma plus it, that's the variable we use here. Now, what's the integral of the sum? Sum of the integral. We're not even going to bother doing it, so then we'll have the sum over n, lambda of n, and then integral 1 over 2 pi I, c minus I infinity to c plus I infinity, x over n to the s, ds over s. Well, if you look at what's going on the right-hand side, we've just dealt with this integral. This is 1 if this quantity is greater than 1. We didn't do that, but that was left as an exercise. It's 0 if this quantity is less than 1, and it's 1/2 if x equals n. So we have two possibilities. One is we can just make sure x is never an integer, or better yet, x is never prime power, and then we'll be okay. Or we can just say, we'll do that one little extra case. So it's not a really big deal. So this side essentially becomes the sum n less than equal to x of lambda of n. Okay, so this is using the results from integral from last time. So integral from last time. And so in a few moments we'll talk about how to estimate a sum like this. Let's look on this side. We're integrating over here. C is probably a large real number so that this makes sense. And we want to push the integration. So maybe we have something like this. Here's 0, here's 1/2, here's 1, here's some value c. And maybe we'll go up to c plus I r, c minus I r. And we'll have some kind of region like this. And then what we want to do is we complete the contour. And when we complete the contour, this integral will be the sum of the residues inside. And the question becomes, where are the residues? Well, the residues occur at the zeros or the poles of the zeta function. We know the location of 1. Where's the first 0 pole we know about? 0, yes.
It has a pole of 1.
It has a pole at 1. And so when s equals 1, this piece is well behaved. This, we know the zeta function has a pole of order 1 or and residue 1 at 1. So we get an x. Now because it's a pole, oops, I dropped the minus sign. Because it's a pole, we get a negative contribution. But we have a minus sign outside, so the pole of the zeta function gives an x. All the other zeros will give a negative x to the row over row. We then have to worry about, there's unfortunately a issue when s equals 0. And we have to worry about the completion of the zeta function. Does that add anything more? I'm not going to go through all those details right now. I want to just give you a sense of what's going on. You can do these calculations and you can see. It turns out the other zeros of this are at the negative even integers, which are well understood, and the negative even integers will give you a negligible contribution from this. And essentially what you get from this side is you get that this is equal to x minus a sum over row of x to the row over row. The sum sadly doesn't converge, or at least it doesn't converge absolutely. So you have to take the zeros in complex conjugate pairs. So the zeros occur symmetrically about the critical line. We are only taking the limit up to maybe minus r. So we would have absolute value of rho less than r. Something along those lines. And because of that, it's only a finite sum, everything will be fine. We can put the zeros in symmetrically, take the limit, everything will be okay. So again, the goal today is to give you a sense of how the tools we've developed in complex analysis are used in analytic number theory without doing an entire course in analytic number theory. If you want to do more about this, if you want to trade some of the homework problems I've assigned with deeper reading in analytic number theory, absolutely happy with that if you haven't done 389. So it now comes down to understanding the analytic continuation of the Riemann zeta function, understanding where the zeros and poles are. That's actually not that bad. Now over here, we don't quite have the sum we want. So it's how do we pass from this sum to the sum we want? So I thought I would just show a few words on that, and then I thought maybe I would prove the Riemann hypothesis for you today. Obviously there will be a mistake. Okay, any questions so far? So what we're seeing is in some sense, very similar to probably generating functions. We're bundling the information we care about, local data, into a global object, and then extracting information from that global object to get information about the thing we care about. There's a lot of fascinating fundamental ideas going on here. So now, let's study the sum n less than or equal to x of lambda of n. Okay? So this is going to be the sum p less than or equal to x of log p plus the sum of p squared less than or equal to x of log p plus plus the sum of p cubed less equal to x log p. Okay? I claim that all this crap over here is negligible in size. What's the highest power of prime we could have?
Log x.
Yeah. So we have p to the k less equal to x. K is less equal to log of x. If you want, log of x base 2. The largest possible k I can take is when p equals 2. So the number of terms I have. Can somebody trivially estimate, who's not in 389, how many prime squareds there are up to x? Trivial estimation. You're thinking too long. Square root of x. We expect the whole thing, the main term was coming from the pole of the Riemann zeta function, was of size x. The Riemann hypothesis says all the other x to the rows, they all have real part 1/2. So all the sum of the x to the row of rows, those should look like square root of x. A trivial estimate is that the square root of x primes here. So if you want, you could say that this part is less equal to x to the 1/2 log x plus x to the 1/3 log x plus, I mean, if we go all the way up to what is the last one? The reason I'm doing this is I can make myself a little bit better. The number of terms I have is log x. If I replace all of them with the largest value, I get x to the 1/2 log of x squared. But if I stop and just replace all of these with the log of x, I get x to the 1/3 log of x squared, which is dominated by this term. And so this is going to be less equal to x to the 1/3 log squared of x. And so by taking an extra step like this, I actually save a logarithm. In this problem, it's not important, but in other things it is. You want to break your analysis and say, here's the main term of the error term, and then here are the error terms of the error term, and then piece them together, and you get less than equal to x to the 1/2 log of x. And this is much less than the main term of x. So this is negligible. So when we're counting primes, it's actually more convenient to not count primes, and not even count weighted primes, but weighted prime powers. Because there are so few prime powers relative to primes, just keep them in play. Okay, so now it comes down to this. So we need to study the sum p less than equal to x of log of p. So the way you often look at stuff like this is you say, well, what regions of x will things not really change that much?
Is that an x or a p?
Oh, sorry, p, yes. I'm jumping ahead of myself. For what regions of x does log p really not change that much? So if I went all the way down to square root of x, if p is of size square root of x, how does log p compare to p around x? About half. So that's a sizable change. So if I truncated this and say, let's say p goes up to square root of x, bound that, and then p goes from square root of x to x, there's a significant change. I will have the right order of magnitude, but it will differ by a lot. So I need to keep p very close to x if I want log p to have very little variation. So what I'm going to do is that this is p less than equal to, say, x over log of x, log p, plus, let me think, do I want to do it this way? I'll do log squared of x, plus the sum x over log squared of x less equal to p less equal to x of log p. So I'm just trying to break p up into places where it doesn't really change that much. Now, in this regime, the log of p is going to still be clearly at most log of x. How many primes are there up to x over log squared of x? Give me a bound. X over log squared x. If every number were a prime, right? So this piece over here would be less than equal to x over log squared of x times log of x, which is x over log of x. And now you can see why I chose a log squared over here. I know that this whole thing is of size x. I want to make sure this is lower. I don't have to do log squared of x. I could have done log to the 1 plus epsilon. I could play all those games. You know, let's just make it easy to write. Now I need to study this thing over here. How much is the primes varying by?
The first term is just log x minus a very small constant.
So it'd be log of x minus the log of log squared of x, which is essentially log x. Right?
So it doesn't change very much.
It
It's by
doesn't
constant.
change very much. Unfortunately, log x is still somewhat sizable. How many numbers do I have in this region? Well, it's the number of primes. If I knew the number of primes was a little bit less than x, you know, the log x would be negligible. If I know I can divide it by x over log x, I'd be fine. But this is not quite enough right now. You know, here we would get log p is clearly going to be less equal to the log of x. We would also get the log of p is greater than equal to the log of x minus, so we have the log of log squared becomes 2 log x, so it becomes the log of 2 plus log x. So minus log of x minus the log of 2. This is slightly significant. If I just try to trivially estimate how many primes there are in this region. So I would need to know how the primes are distributed. So again, this is a little bit interesting because I actually I care, but today I don't care about proving the prime number theorem. I care more about showing techniques, showing how you would attack things, showing how you would refine things. If we tried breaking it up like this, there's too much variation. What we would have to do is maybe break this interval up into, yes?
Confused. Can't we write this as 1 minus epsilon times log x for all epsilon greater than 0 and get the right main term?
Alright, what do you want to do?
Just the log p you can bound above and below by log x times 1 plus epsilon, or well, by log x and log x times 1 minus epsilon for all epsilon greater than 0, and that'll give you the right main term. Like that'll give you a constant 1. Because log x
Okay.
minus, yeah.
And so what you want to say is that when x becomes very, very large,
Yeah.
you can make this within an epsilon.
Yeah.
Yes. So if people want, I will show how to do that argument. Right now I'm trying to just show why naive arguments fail.
Oh, okay. Okay.
And you can then refine it. And that's exactly how you can do this. And just say, really what we want to do is look at this as the log of x times 1 minus log of x over log of x. And if you write it like that, when x becomes really, really large, you can make log x over log x with an epsilon of 0. And then all of these numbers are log of x times a quantity of at most 1 minus epsilon for epsilon small. And then you would use that to get that this sum is essentially what you want. The other way of saying this is that most of the primes are going to be coming towards the end, which is not so surprising as you are expanding and going across orders. So again, right now the idea is to just show you how you would attack things, how you would break things up. Number theorists are really like accountants. Bookkeeping, keeping track of main terms, low order terms. Where do you split things? Where do you have your free parameters? How do you divide things up? What's the main term? What's the other term? Over here, when you write it like this is very hard to work with. But if you pull out the log of x, now you see, the log of p is at most log of x, and it's at least log of x times 1 minus epsilon, where I can make epsilon arbitrarily small. And then I would then get that this sum, if I now pull out the log p, I would now get essentially the number of primes between x over log squared of x and x is going to be of size x divided by log of x, right? Because this whole thing is of size x. From the contour integral, we divide by the log of x. And if the number of primes in this region is essentially x over log x, and the number of primes up here, well, how many primes could be at most x over log squared of x? Trivial estimate for how many primes could be at most x over log squared of x. Yes, x over log squared of x. And so if I show the number of primes in this region looks like x over log x, and I know the number of primes up to here is at most x over log squared, then the number of primes from the very beginning to x is also at most x over log x. So if you go through the arguments, if you can just understand this region well enough, you actually can count how many primes there are with really good accuracy. Okay, so I don't want to go into too much detail. I'm hoping that this gives you some idea of how we use the tools from complex analysis, why these are useful, why we take these logarithmic derivatives, why this is a great way to attack problems, why the Euler product is so important in number theory, why we don't count all primes equally. As you go higher and higher in mathematics, you actually want to put weights on the objects you study. These weights are designed to facilitate the computations you need to do. Okay, any questions on this? Would you like to see proof of the Riemann hypothesis now? So, one free homework exemption problem to the first person to catch the mistake. An A+ in this class and admission to Princeton, if you can make the argument work. If you would like to replace Princeton with another school, that should be fine. I do have the ability to get anybody into Princeton. The problem is I can only use this on people who are qualified to get into Princeton, because if I ever use it for somebody else, I lose that right. So it's not necessarily the greatest power to have. So zeta of s is the product over all primes of 1 minus 1 over p to the s inverse. And we can continue to the real part of s greater than 0. What I'm going to do now is I'm going to look at a sequence of modifications. So zeta 2 of s is going to be 1 minus 1 over 2 to the s divided by 1 minus 1 over 2 to the 2s times zeta of s. Can this function be analytically continued? Yeah, zeta can be analytically continued. This is a really nice object here. The 1 minus 1 over 2 to the s cancels the p equals 2. And so if you want to write this out, it's 1 minus 1 over 2 to the 2s inverse 1 minus 1 over 3 to the s inverse 1 minus 1 over 5 to the s inverse dot 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 dot. I've basically just replaced the very first one of 1 over 2 to the s with 1 over 2 to the 2s. Have I introduced any new zeros or poles? Where would the numerator be 0?
S equals 0.
S equals 0. Where would the denominator be 0? Okay, so as long as I stay away from s equals 0, I'm fine. I'm in a region where that's not going to be a problem. And this function can be analytically continued. In terms of the zeros of zeta 2 of s and the zeros of zeta of s, are there any differences in the location of zeros for the real part of s greater than 0? Do they have same zeros for real part of s greater than 0? The only way that these can vanish is I need this quantity here to have absolute value 1. To have absolute value 1, s has to have real part 0. So do we agree that they have the same zeros for real part of s greater than 0? Any dispute? We're not that far away from proving Riemann. If it's correct, I will split the prize money, but only with the people who are in class today. What do you think zeta 3 of s should be?
One minus 1 over 3 of s.
So 1 minus 1 over 3 to the s divided by 1 minus 1 over 3 to the 2s. Zeta 2 of s. And so now this will be 1 minus 1 over 2 to the 2s inverse. 1 minus 1 over 3 to the 2s inverse. 1 minus 1 over 5 to the s inverse. We agree, same zeros for real part of s greater than 0. Everybody agree?
I feel like we shouldn't.
Well, I mean, normally it's at some point something wrong happens. The question is, have I reached that?
Looks correct.
Okay.
Wait, can we only use this formula when the real part of s is greater than 1? Like you can continue the function.
So let's take real part of s greater than 2. You know, let's study it in a region where we're absolutely fine, everything is fine. So, by induction, we'll continue and say zeta of n plus 1 of s will be 1 minus 1 over the n plus first prime of s divided by 1 minus 1 over the n plus first prime of 2s. Zeta n of s. What can we say about the zeros? Same zeros. As zeta of s. So now let's look at the limit as n goes to infinity of zeta of ns. Yes?
But then you're taking an infinite product.
Well, for each function, I'm taking the limit of my functions.
But an infinite product can vanish without the numerator vanishing.
But I could take these infinite products and I can write them as a series expansion, where the real part of s is greater than 2. I have functions that converge nicely when the real part of s is greater than 2. There's actually a really nice formula for this limit. Can anybody tell me what the limit is as n goes to infinity of zeta n of s?
Zeta of 2s.
Zeta of 2s. This limit exists. Okay. If I take the limit as n goes to infinity, this is converging to zeta of 2s. We know zeta has no zeros if the real part of s is greater than 1. Okay? I don't think we've proved that in class. It's not so bad. So claim zeta of s does not equal 0 if the real part of s is greater than 1. So I'll leave that as an exercise. I don't want to go too much into all the number theory calculations or not. If you want to do this instead of one of the standard homework problems, that's fine so long as you have not taken 389 with me. It's not hard to prove if s is a real number. Because if s is a real number, you have 1 plus 1 over 2 to the s. There's no way you're summing positive things. So the only chance you would have is if s is complex, you could have somehow things oscillating. And you would use the Euler product. So use Euler product. So let's just accept this claim for now. This claim is true. I promise you this claim is true. There are 2 students in here who've taken 389 with me. They can vouch for this, that we have proven that this is true. What do we know about the zeros of zeta of 2s? if zeta is not 0, if zeta of s is not 0 if the real part of s is greater than 1, what can you tell me about zeta of 2s?
It's not 0 if the real part of s is greater than half.
They're not 0 if the real part of 2s is greater than 1, i.e. the real part of s is greater than 1/2. They have the same zeros. Yes?
But you could also replace the greater than 1 with the greater than or equal to 1. And that would imply it has no zeros. For zeta of 2s.
Well, the real trouble is, rather than replacing this with a p to the 2s, I could do p to the 3s, and this would become a zeta of 3s.
Yeah.
And if it's a zeta of 3s, then that would mean the Riemann zeta function has no zeros with real part greater than a third. Which is clearly wrong, so clearly something is wrong here. So if you want, you can actually prove the Riemann zeta function has no zeros at all. Which contradicts the fact that it has infinitely many zeros, a critical line, which we've known for quite a while now. So there must be a mistake somewhere. Because you can strengthen this argument to prove that the zeta function has no zeros in the critical strip.
Just because the zeros agree for each finite step, does that mean they agree in the limit?
Good question. What do you think?
No.
No. The limit of the analytic continuation is not the analytic continuation of the limit. The limit, the analytic continuation, is not the analytic continuation of the limit. I think that's the easiest way to phrase what's going on here. Is we've got to be very careful about how we deal with interchanges and limits. So we know that at every n, zeta of n and zeta of s have the same zeros. So if you have 0 for each n, it seems like as you let n go to infinity, you're not going to lose any of those zeros. You may pick up additional zeros, but you shouldn't lose any zeros. So there's a lot of really good stuff to think about here as to how the hell can this be happening? You know, we're going to be working in the region where the real part of s is greater than 2. And again, there is no way to salvage this argument, okay? This argument is fundamentally flawed. There is no way. I just want to make sure in case this video ever gets out, I want to be able to point to the entire clip, because I know when politicians speak, they focus on one small subset. I want to be perfectly clear. Hello, readers, listeners. I do not believe this method can be salvaged at all. I believe it is fundamentally flawed. But there's a really good lesson here about the dangers of interchange. Is we get very careless. And we always think, oh, we can just interchange them. We can be justified by an advanced class. Not always. So if anybody wants to, I would be willing to count this either as a project if you want like 5 or 10% of your grade, or as multiple homework problems. I have some notes about this problem. Write this up as a really nice article for like a general, undergraduate or just general interest math magazine about the dangers of interchanging limits. And this is something students do not have sufficient experience with, because we often gloss over this in the introductory classes. And we often say, oh, in a higher level, and we don't really highlight the examples where you can't. Now, for Fubini's theorem, sometimes you get an instructor who will tell you, here's an example of why you can't interchange the limits. Have you all seen an example of where you can't interchange Fubini? I try to work this into almost all my classes. Is anybody here who's not seen a situation where you cannot interchange the order of sums? Okay, so let me give you a quick example. So the sum over mn of amn is not necessarily the sum over nm of amn. So somebody who's had me before, what sequence am I using?
Oh.
Alright, so that seems to have So I'll just do it really fast. Plus 1, minus 1, 0, 0, 0, 0, plus 1, minus 1, 0, 0, 0, 0, plus 1, minus 1, 0, etc., etc. And you see if you do all the vertical sums, each vertical sum is 0, and then if you sum the vertical sums, you get 0. But if you do the horizontal sums, all the horizontal sums are 0 except the first, which is 1. And so this is an example where you cannot interchange. And the problem is if you put in the absolute value, the double sum of the absolute value is infinite. And that's why you can't necessarily interchange. If the double sum of the absolute value is finite, then you can interchange. Okay, so again, I wanted this to be somewhat of an interesting surprise as to just how easy it is. Now, the advantage of looking at a problem like this is if you have a proof of the Riemann hypothesis, you're going to know you should stop and look at it very carefully. Not every mathematician does, unfortunately. They do submit stuff like this all the time, which I sometimes have the joys of reading. But over here, when you're looking at these arguments, you want to try to get a sense, is this plausible? Is this believable? And in the argument over here, not only are we able to prove the Riemann hypothesis, we can prove something even stronger, that it has no zeros. So we know we've made a mistake. So again, it's always a question of why am I choosing to talk about this in class as opposed to other things? Most of you are not going to try to prove the Riemann hypothesis with your lives. I think this is a good choice. It's fine to just play with it a little bit, at home. Don't tell people you're working on it. That's fine. But when you're attacking things in life, you want to get some sense. Can you trust your answer? Does this seem plausible? Does this seem reasonable? Do you buy this? What kind of tests can you do? Fundamentally, why can you justify it? This seems really plausible. At each stage, this is true. I'm taking the limit. There's got to be some kind of convergence going on here. This is converging to zeta of 2s. What breaks down? If you want a really good project, going through this carefully and trying to figure out what is wrong here. There's a lot of really valuable stuff. Okay, any questions about proving the Riemann hypothesis? All right, so I want to end today by just briefly stating the Fourier transform. So we are going to need this in the next part of the course. We're going to shift into either stationary phase and then central limit theorem, or central limit theorem and then stationary phase. Probably stationary phase first. So given a function f of x, which would be nice, f hat of c, and this would be the Fourier transform. Sorry, is going to be the integral from minus infinity to infinity of f of x e to the negative 2 pi I xc dc.
Sorry, what the heck is that?
It's a Greek c.
Okay.
And the advantage of being in the world of tech is I can just write the tech code for what we're doing. Some people use the letter y. I don't want to use the letter y because we're going to be having a complex variable soon. Okay? And so the question just becomes, for what values of f does this converge? This is very much related to what we were just doing. What can you tell me about the absolute value of e to the negative 2 pi I xc?
It's 1.
It's 1. So for instance, if f is non-negative, if f is a probability density, always exists. So always exists if f is a probability density, or if the absolute value of f is integrable. And in those cases, the Fourier transform will always exist. For those of you who've done probability, this is very similar to the moment generating function. It's the moment generating function essentially evaluated at a complex argument. It has the advantage of always existing. The moment generating function does not always exist. If you have a choice, work with something that exists. So as a nice exercise to think about, I want you to try to calculate the Fourier transform of e to the negative x squared over 2. So try to see if you can figure out what is the Fourier transform of that function for Monday. All right. Have a good weekend.